Hi everybody. So in this video we're going to continue with Chapter 1, Number and Algebra Basics, specifically Section 1.4, Exponents and Logarithms. So we know what exponents are. For example, we can solve something very simple, like 2 to the power of 3. We know that 2 to the power of 3 is equal to 8, because 2 times 2 times 2 is equal to 8. If we were asked to express this in logarithmic form, this is what we would have to do. First, we have to identify the base. So here we have a base, which is 2. So this is the base. Then this is the exponent. That's the exponent, 3. And this would be normally the solution. So a logarithm is the same as this, but expressed in an opposite way. So what do I mean by that? Well, you would write this in logarithmic form, saying, well, logarithm of base 2 of 8 is equal to 3. So notice that we can apply something here, a little trick called the heart trick. And I'm going to try to draw a heart. If we go like this, we go 2 to the 3 and then to the 8, we get sort of a heart shape. So what does this mean? Well, it means that 2 to the 3, starting from 2 going through 3, 2 to the 3, is equal to 8. So notice that this is the inverse of this expression here. So the inverse of 2 to the 3 equals 8 would be log base 2 of 8 is equal to 3. Okay, so in general, if we have that y is equal to a to the x, then we can express this in logarithmic form by saying that x is equal to log base a of y. So two very common logarithms or logarithmic bases are log base 10, log base 10. It is so common that normally you're not going to see it written like this in documents. It's simply going to be written as log. So log with no base, you can assume immediately that this is log base 10. Another common logarithm is the natural logarithm, which is written as ln. And basically, the natural logarithm is a logarithm of base e. What is e? Well, that's Euler's number. If you don't know what Euler's number is, it would be good for you to do some investigation on what is Euler's number. Then, one thing to note here is that this notation is never used. I'm just using this as an illustration. Log base c is the natural logarithm, and it's written like this. Both the natural logarithm and logarithm base 10 have many practical uses in the sciences, so it's very important to learn a little bit about them. So on the next slide, you're going to find a couple of examples to help us illustrate how to use logarithms. So first it says, write 2 to the power of 3 equals 8 in logarithmic form. We already did this, and we said that this would be log. Then we write the base. Remember that this is the base. Log base 2 of 8, which would normally be the answer for the power. Log base 2 of 8 is equal to 3. And then you can always check if you have the right answer by going 2 to the 3 is equal to 8. Some people like to call this the heart rule, and it's just a trick for the memory, right? Then we have another example that says write log base 3 of 81 equal to 4 in exponent form. So here we can just apply the heart rule, right? We'll go from here to here and there. So that means that 3 to the power of 4 is equal to 81. So this is actually true, right? So that would be changing the logarithm to exponent or exponent form and changing the exponent form to logarithmic form. So on the next slide, we're going to find a few more examples. And then it says solve these equations for x. So letter A says x is equal to log base 16 of 4. Now, let's just rewrite this as this equaling x, and the only reason I'm doing that is because I want to use the heart rule to solve for x. Change this into an exponent form, which is easier to solve for us. So we would say, okay, 16 to the power of x is equal to 4. So let's write it that way. So 16 to the power of x is equal to 4. But we can rewrite 16 as 4 to the power of 2, right? Because 4 times 4 is 16. So we can say that this is 4 squared to the power of x is equal to 4. And then we can say, well, because this exponent is below this other one, which is to the power of x, we multiply, right? The rule is multiply. So we would get 4 to the power of 2x is equal to 4. So what do we do next? Well, remember that 4 by itself is like saying 4 to the 1. So once you have this situation where you have the same base on both sides of an equality, you can say, well, this doesn't matter anymore because it's just 4 to the power of something. The solution will be in the exponents. So the solution to this equation will be 2x is equal to 1, and then we simply divide both sides, and we get x is equal to 1/2. So for B, they have the expression log base 7 of x is equal to 2. So using the heart rule, we say, well, 7 to the power of 2 is equal to x. So 7 to the power of 2 is equal to x. Therefore, x is equal to 7 squared, which is 49. Remember to always get to these solutions with numbers and exponents all the way to the end. You don't want to leave it in the exponent form. Now let's do C. So for C, it says log base B of 1 is equal to x. Now don't be impressed by having another variable like b. Just treat it like a number. So because b is a constant, since we only have to solve for x. And all we have to do is use the what I call the heart rule. So we go b to the power of x is equal to 1. So if we rewrite that in exponent form, it would be b to the x is equal to 1. So we don't have to really know what b is because there's a general rule that says that any number to the power of 0 is equal to 1, as you recall. So then x can only be 0 and b can be anything, any value. So for D, we have log base x of 32 is equal to 5/2. So again, doing the heart rule, we would say x to the 5/2 is equal to 32. So let's rewrite it in exponential form. X to the power of 5/2 is equal to 32. So how do we do this? Well, remember that these equations can only be solved when you have the same base. And in this case, this base is x, and this base would be probably 2, because if we factor 32, let's see what we get. We're going to go 2 times 16, 2 times 8, 2 times 4, 2 times 2, and 2 times 1. So we have 1, 2, 3, 4, 5. So 32 is 2 to the 5. So then we get x to the power of 5/2 is equal to 2 to the 5. But since we don't really have to solve for the exponents, it doesn't really matter that we don't have the same base as in previous cases, right? We don't have an x value in the exponent, so we just have to solve for x. In other words, we need to change this exponent to 1. So we get x to the 1, which is x, would equal some value here to the right. So how do we do that? Well, this can be done by using a simple trick. ask yourselves, what number multiplied by 5/2, what number, question mark here, is equal to 1? Well, that number would be the reciprocal. So what is the reciprocal? Well, the reciprocal is the same number, but backwards, because 5/2 times 2/5 is equal to 1. How so? Well, if you have 5 times 2 is 10, divided by 2 times 5, which is 10, you got 10 over 10, and that equals 1. And you can test this with any number times its reciprocal, and you're going to get 1. So we use the reciprocal to use it as an exponent on top of this one. So we would write x to the power of 5/2 to the 2/5. But we cannot just do that to one side of the equality. We would have to do this exact same thing to the other side of the equality. So we go this to the power of 2/5. 2/5. So then what do we get? Now, we didn't alter the equality because we did the exact same thing to both sides of it. What are we going to get then? We're going to get x to the power of 5/2 times 2/5 is equal to 2 to the 5 times 2/5. Remember that when you multiply by fractions, you multiply by the top number and divide by the bottom number, right? So what happens here? Well, remember that this is the reciprocal. So 5 times 2 is 10, 2 times 5 is 10. So this just cancels out and becomes 1. So x to the 1 is just x. So we get x is equal to, and then here we can cancel the 5's because they're dividing, and it's going to be 2 to the 2, which is 2 to the 2, which is 4. So this would be the solution. Next, we're going to do example 1.22. And it says, earthquake magnitudes R are measured on the Richter scale. I don't know if you guys have heard about the Richter scale, which is used to measure the intensity of an earthquake. And it says, which is a base 10 logarithmic scale, and relative comparisons are useful. For example, an earthquake of magnitude R equals 4 is 10 times as strong as an earthquake of magnitude R equals 3. So what does that mean? Well, this is a base 10 scale. So if you have that R is equal to 4, the intensity of the earthquake is 10 to the power of R. So in this case, it would be 10 to the power of 4. That would be one earthquake. Then the other earthquake had a magnitude of 3, so that would be 10 to the power of 3. So comparatively speaking, this earthquake is obviously 10 times stronger than this earthquake. How do we know that? Well, because 10 to the 4 divided by 10 to the 3 would tell us how many more times intense this is from this. And recall that this is 10 to the power of 1, which is 10, right? Because 4 minus 3 is 1. So 10 times stronger. That means that this earthquake here is 10 times stronger than that one. The question in the example is, what is the magnitude of an earthquake R1 that is twice as strong, as another of magnitude equal to R equals 3? So earthquake with a magnitude of R1, that would be 10 to the power of R1. So that's what we have to solve for, 10 to the power of R1. And it says that it is twice as strong as another one of magnitude R equal to 3. So that would be divided by 10 to the 3. And because it's twice as strong, it means that this would equal 2, right? Because this is double that. So if this one is twice as strong, it means that this divided by that equals 2. So this is what we have to solve for. So how do we solve this? Notice that we can write this as 10 to the power of R1 is equal to 2 times 10 to the power of 3. Now you can say, well, this is just 2000. Yes, but that's not the solution yet, right? Because we have 10 to the R1. So that means that we have to express this in logarithmic form and solve it. So this is base 10. So log base 10, remember that you just write log, because that's log base 10. So here we could use the heart rule, but backwards, right? So we could say base 10, because this is 10 to the R equals 1. Remember that we could do the heart rule, but backwards. So we would say, let's just draw the heart, and let's sort of like that, right? So we would say log base 10 of the answer, right? 2 times 10 to the 3 is equal to R1. So log base 10 of 2 times 10 to the 3 is R1. Notice that if we do the heart rule again, we would go back to the previous expression, right? 10 to the power of R1 is equal to 2 to the power, or 2 times 10 to the power of 3. So why do we do that? Why are we solving it this way? Because by changing it into a logarithm, we can use this here and plug it in the calculator to get the solution. And that's what we're going to do next. So here we are with a calculator. And remember that we want to solve log base 10 of 2 times 10 to the 3. Now recall that I said that because this logarithm is so common, we don't actually write the base 10. So let's eliminate that. But we know that this is base 10. Now in the calculator, you are going to find a button that says log, and it's right here next to number 7. So log is logarithm, base 10. Notice that they don't write base 10, but that's what it is. And then we type 2 times 10, power button, to the power of 3. Then we have to move it to the right a little bit, close the parenthesis, and hit enter. And we get 3.301.